today we will start about discussing about some devices which belong to the same family of FETs, but construction wise or operating principle wise they are quite different than the FETs. So you will understand that how JFET and the devices that we will discuss today, which are called MOSFETs, are similar in some aspects and also not similar in several different aspects. So let me just share my screen with you and start our discussions on MOSFETs. Can you see my screen?
Yes, ma'am, it's visible.
Yes, ma'am.
Okay. So we are still discussing field effect transistors, but we are starting to discuss about a new subfamily, so to say, MOSFETs. Okay, so we as you already know that we are done with JFETs, and now this device MOSFET, its full name is metal oxide semiconductor. The MOS stands for metal oxide semiconductor, and FET is still field effect transistors. Okay, so MOSFETs are basically of two types. One is called depletion type MOSFET. So ignore this C, depletion type MOSFET. And another one is called enhancement type MOSFET. One by one, we will talk about both of these devices. And both of the devices can be N channel and P channel, just like our JFETs. It could be N channel or P channel device. So let me just start by discussing about an N channel enhancement type MOSFET, and one by one we will cover all these four devices: N channel enhancement type, N channel depletion type, and the P channel variants of that. So if I start by talking about the construction of an N channel E MOSFET, then the structure is the first basis of the structure is basically a p-type material. So we are talking about an N-channel enhancement type MOSFET, and its base material is called a substrate or body. We call it a substrate or body, and this is basically made of a p-type material. So p-type semiconductor. On that p-type semiconductor, we create two regions. We create two regions which are N-type by doping them to be N-type on that substrate only. Okay, so the two portions, you can assume them as grooves kind of a thing. So you create two grooves and you dope them with N-type material, and you create these two wells made of N-type material. Okay, so this is the base structure of your N-channel E-MOSFET. Now the terminals will be, one will come out of this N-type groove that I had in one side, and we can call that source, and the other one we'll call it drain. So they are like reversible. You can call either one of them as source or drain. It does not matter. So two of them are exactly identical, and if we drag out two terminals out of them, we call one of them source, one of them drain. Okay, and one terminal also comes out of the body or substrate, and this is called the body terminal or SS terminal. Substrate is sometimes also called SS terminal. Okay, so these are the three terminals, but yet we have not talked about any gate, right? So the same three terminals, source, drain, and gate, we can expect in these devices as well, because these are also field effect transistor. Here also the same thing will happen. We will apply a voltage VGS and will control the flow through that voltage. So that phenomena is going to be common here as well. But where is the gate terminal? So before we have the gate terminal, we have the most important component of this device, which is a oxide. So we have a silicon oxide layer, which is very, very thin. Okay, so it's a very thin coating. You can imagine it's not a layer, it is basically a coating of the order of 1000 angstrom or so. It's a very thin layer of silicon oxide, and this is an insulator. Okay, so silicon oxide, all the oxides are usually insulators, you know that, right? So this silicon oxide is also an insulator, and this is coated through the region where this N-type material ends and this N-type material starts. Okay, this entire region is coated with silicon oxide layer, which is quite thin, very thin, but still it's an insulator. Okay. Next, on top of that, I have a metal layer. So this black thing that I have drawn here is basically a metal layer, and this is this M, right? So M, metal oxide semiconductor, and thus the name, metal oxide semiconductor field effect transistors. So the terminal that comes out of that metal is basically my gate. Okay, so here the most important thing to see is that the gate terminal is not in contact with the semiconductor chunk that I have, the body or the substrate or source and drain. It is not in contact electrically speaking, because we have a layer of insulator sitting in between. So that is why this entire family of MOSFETs are also called insulated gate FETs. Insulated gate FETs, because the gate terminal is basically insulated from the entire device via a silicon oxide layer. So this is basically the construction of an N-channel enhancement type MOSFET. Now the first question that should come to your mind is that where is the channel, right? I have an N-type material which is connected as source, another N-type material which is connected as drain, but I don't see any channel there, but I'm calling the device an N-channel E-MOSFET, right? So where is the channel? Now that is why the name enhancement MOSFET. So this device is different from the devices that we have discussed as JFET, because here we do not have any channel to begin with. We do not have any channel to begin with, but that channel gets enhanced as you apply proper biasing to the system. Okay, so today we will just try to understand the working principle of this device and try to incorporate that idea to the output characteristics to understand that how this device can work. So let us start by seeing that how this channel can get created, get enhanced if I apply proper voltages in these terminals that I have. Okay, so this is the structure. So in 3D, if you want to imagine, this is the structure in 3D where I was talking about these wells. So these are these wells where you have created the source and the drain terminal. Okay, so now let us talk about biasing. So the device works on basis of the gate to source voltage, as it has worked in case of our JFETs. But this time we start the biasing by between the gate and the body terminal. So the first thing that we do to understand the working principle is to connect the battery so that the gate terminal becomes positive and the body terminal becomes negative. Okay, so just imagine that I have connected a battery between gate and body terminals so that the gate is positive and the body terminal is negative. Okay, so if I have a scenario like this, then what will happen? A current will try to flow right in the circuit because you have attached a battery here. But we have an insulator layer sitting in between. That means current cannot flow. Fine, because I have an insulator sitting in between, the current cannot flow. So if you just look into this device where you have one metal layer and another semiconductor which is also can conduct some electricity, separated by an insulator layer, what general electrical component comes into your mind where you see two conductors separated by an insulator? Two conductor plates separated by an insulator. What is that?
Capacitor.
Capacitor.
Right, capacitor. Very good. So it should work like a capacitor because current cannot flow, right? DC, if I connect a battery in a capacitor, it does not, current cannot flow. But what happens? The capacitor gets charged, right? That happens. So similar kind of an effect I can imagine here. So what will happen in practice is that because this side is positive, right? So this is a p-type substrate, and the p-type substrate, though have majority of holes, it has some electrons. Some electrons are here, which are minority carriers. So electrons are here in the p-type substrate as minorities, right? So these electrons, which are type substrate, will try to move towards the positive battery terminal like this. Okay, so they will try to move because they are attracted towards this positive terminal. They will try to move this way, but they cannot because the insulator layer is sitting here. So what will happen? Gradually, the electrons will get crowded near this top surface of the semiconductor that I have. So this region will slightly be gaining more and more electrons because they are willing to flow in that direction, but that is not being possible because of this insulator layer sitting here. Okay, and at the same time, what happens is the holes that we have in this p-type substrate, they are attracted towards this negative terminal, and they will be pushed down, right? They will be pushed down. So effectively, what you will have is a capacitor-like effect where lots of electrons will be crowding on the top surface here near the semiconductor material. They cannot leave the p-type substrate because the insulator is sitting here. So just near the top surface, we'll have a huge crowding of electrons. So let us just think that what is happening. We had a p-type substrate. So this entire thing drawn in light blue, this entire thing should be behaving like a p-type material. But gradually near this top surface, I am having a crowding of electrons and removal of holes. So as the number of holes go down and the number of electrons go up, gradually this p-type material starts behaving as if it has equal number of holes and electrons. No one is majority, no one is minority, because electrons are constantly growing and the holes are constantly decreasing. Now, if I increase this voltage a little bit further, then the number of electrons here will be more than the holes, right? This phenomena is called inversion. So a small layer near this top surface of this substrate, where the insulator is being covered on top, is coated on top, here you will have a huge crowding of electrons, and gradually that portion will start behaving like an N-type material. Though it's a p-type substrate, constant gaining of electron and constant loss of holes will make that portion behaving like an N-type material, and gradually a channel will open up between the source and the drain. Okay, because this portion that I have behaving like an N-type material, it is not a p-type material anymore, because here you have quite a large number of electrons. Electrons are majority there and holes are minority because they are pushed down. Okay, this is how the oxide layer helps in creating a channel where there was no channel to begin with. Okay, so this is called the phenomena of enhancement of channel through the inversion that occurred because you applied a voltage between gate and body. So is this idea clear, that how the channel gets enhanced? Do you have any question on this? Any doubts? Okay, right? Okay, fine. So this is how the channel gets enhanced. And so from here you can understand that first to begin with, there was no channel, and a little bit amount of voltage is used to cause the inversion phenomena, right? So that first few small voltage that we have applied between gate and body will be used to create the channel in the first place. There was no channel to begin with, so to cause the inversion phenomena, you need a little bit of voltage, and that voltage is called a threshold voltage. Below that, there is no channel, so there is no current flow, and thus an enhancement type MOSFET is basically remains off. So it's a basically off device if not biased. If not biased properly, an enhancement type MOSFET is basically an off device. You have to apply proper biasing so that the channel gets opened and the current can flow. So the rest of the story is quite similar to what we had previously. I must connect a battery between drain and source, right, to attract these electrons which are sitting in source to make them flow to the drain. I attach a battery between drain and source, where the drain terminal I have kept as positive, just as before. So now as the channel got enhanced, the current now can flow, electrons will flow, and the current will also flow in the appropriate direction. Okay, so this is my VDS. That was VDS in my JFET. A similar type of battery is attached here as well. This is also called VDS, causing the drain current ID. Okay, so one more thing that we do here is that in this case, you can see that the body terminal is attached to the negative side of the battery, right? So this could be considered as the ground. And here the source terminal is connected to the battery. Now, if I still apply another voltage between source and body, that is useless, right? Because the biasing that I need is already done. So to avoid any more further biasing voltages present, what we do is we short circuit the source and the body. So that makes a common ground terminal at the body or source. And you can assume this to be your ground, right? So both the substrate and the source are at same voltage now, and you can take the source as a reference. Just like JFET, you can take source as a reference and see that gate or drain at a higher voltage than source. So in a consolidated form, this will be your structure, right? So you can assume that instead of connecting a battery between body and gate, you connected the battery, the previous battery, this one only, right? This one only, where you had gate terminal positive and body terminal negative. We just connected that between source and gate now, because the body and source are short circuited. Okay, so this is the entire biasing of E-type NMOS. So E-type NMOS has source and the body short circuited. Sometimes the device comes from the market in that way only, where you don't have to connect them, short circuit them from outside. They're already short circuited inside the device. So you just connect your VGS battery, the controlling voltage that will open up the channel between source and gate, and your current flow, the voltage responsible for the current flow VDS between the drain and the source. So here we will be using the same terminology as we have used in JFET, that is convenient for you as well to use to understand that VDS is the output voltage here also, ID is the output current, VGS is the input voltage or the control voltage. So we are not using terminologies like VGB, like gate to body or gate to substrate, VGSS. We are not using those. We are just using VGS, and that to just maintain the consistency with whatever we have discussed in JFET. Similar names we are using here. Okay, so here VGS is my input voltage, VDS is my output voltage, and ID, the current flowing in the output circuit, is my output current. So any questions up to this point? Fine. Okay.
Yes, ma'am.
Okay, so let me just move forward then. Now let us try to understand it more in a more quantitative way, so that we can draw the output characteristics now. Okay, so this thing I have already defined, but let us just concretely define threshold voltage once again. So threshold voltage is denoted by VT, and that is the minimum VGS required to open up the channel in the first place. Okay, so until your VGS is equal to VT, you do not have any channel. So the initial so suppose I have a device whose VT is 2 volts. Okay, so if VT is 2 volts, that means that unless your VGS is more than 2 volts, you cannot have a channel there. So the device will remain off for that time. Now, if I have VGS equal to 3 volts, then 3 minus 2, that is the threshold voltage, 3 minus 2, that 1 volt will be contributing to the channel width. So VGS increases, and thus the channel width also increases, and the excess voltage that I have, VGS minus VT, is basically contributing to how big my channel will be. The first VT amount goes just to cause the inversion, and next the channel gets wide and wide and wide as you go on increasing VGS. Okay, so this is how we define the threshold voltage. Now we will do a kind of a similar exercise as we did in case of JFETs to understand or to draw the output characteristics. So to understand the output, let me just focus on something which is basically the voltage difference between gate and the drain terminal. Why am I doing that? Because you will see that this is going to be a very interesting way to understand that how the channel width gets controlled and how the drain to source voltage affects the channel width. Okay, so let us just look for this voltage VGD, that is the voltage difference between gate terminal and the drain terminal. Okay, So VGD, the voltage difference between gate and drain, we can measure that with reference to the source, right? So gate is at a voltage VGS higher than source and drain is at a voltage VDS higher than source. That means VGD would be VGS minus VDS. You can also figure it out by Kirchhoff's law, KVL, like Kirchhoff's voltage law. You will see that we have two batteries in this loop. If you start from gate terminal, you go through this path, following these two, crossing these two voltage sources and reach the drain terminal. You will see that VGS and VDS are in opposite polarity if I travel through this path, right? If I just travel through this path and calculate, write down the voltage sources I come across using Kirchhoff's voltage law, you will see that VGD is equal to VGS minus VDS, okay? So this is the voltage difference that I have between gate and drain. So now keeping this equation in mind, and this is going to be the key equation in understanding the behavior of the channel width, we will proceed for different values of VDS. So the first case that I consider is VDS equal to 0. So let us take it slow here a little bit. VDS equal to 0. That means this voltage that I have here, I don't have it. Okay, I don't have any voltage source here. That means what? That means there is no voltage to attract these electrons from source to drain. Okay, so there is no voltage effectively to attract the electrons from source to drain. So then what happens? In this scenario, if I look at this equation, okay, if I look at this equation, then I see that VDS is equal to 0, right? So that means VGD is equal to VGS. VGD is equal to VGS. What does it mean? That simply means that the left side of the channel between gate and source and the right side of the channel between drain and source are having similar amount of biasing present there. Okay, just keep in mind that I need at least V threshold amount of voltage to open up the channel. So if VGS and VGD are both same, then whatever voltage I have applied in VGS, the same voltage is effectively being applied between VGD. So if I have a channel opened up in the left side of the of this circuit from gate, on the right side also I have a channel because it is more than VT and it is equally more than VT. Right? It's equally more than the threshold voltage. That simply means that my channel will be uniform on both sides from this point. So from gate point onwards, right side and left side has equal amount of biasing and thus the channel is going to be uniform. So whatever the value of VGS is, say threshold is 2, VGS is 3, then VGD is also 3, right? And that means the excess voltage 1 volt will be contributing to make the channel effective width of the channel. So that width is going to be same on both sides. Okay, but this scenario changes if I now start increasing VDS. So VDS was 0. That means there was no current flowing in the circuit because there was no voltage to attract those carriers to the other side of the circuit, right? So in this point, the channel was also uniform. But as soon as I start increasing the voltage VDS, let us make VDS a little bit positive because I need positive voltage to attract those electrons. I need positive voltage to attract those electrons. The current will start flowing. Definitely the current will start flowing. But at the same time, something else is also going to happen. Now VGD is no more equal to VGS, right? Because you have some positive value sitting here. VDS is greater than 0. Say VDS is equal to 2 or 3. So that value comes and sits here. And that means VGS, whatever the value that you have applied from this battery, that get reduced. And the other half of the channel is not getting equal amount of biasing. Okay, so that is the key point to understand here. Now threshold voltage is same, the device is same, the material is same, and the threshold voltage is same. And I am overcoming that threshold voltage by applying this VGS on the left side of the circuit. But on the right side of the circuit, that effective voltage is coming down because the drain to source voltage is positive. So this drain to source voltage is contributing to reduce the effective voltage on the right side of this circuit, and near the drain terminal now the voltage that I have is not exactly equal to VGS, but it is less than VGS. Okay, so it is less than VGS. That means the effective channel width will also be a bit less. So what I can expect is right after the midpoint, the channel width will be a little bit less than whatever I had on the left side. So is this point clear? Is this point clear? That why the channel width is started to shrink as soon as VDS is positive? Okay. So the gate and the drain, between the gate terminal and the drain terminal, the effective voltage is now smaller than whatever is applied between source and gate. Okay, gate to source, VGS. And that is reduced by the amount of VDS. So the channel starts shrinking on the right side. While the channel is quite big on the left side, the channel starts shrinking on the right side of the circuit. Now you can see that which way I am heading, right? So there must be a critical value. There must be a critical value as you go on increasing VDS. As you go on increasing VDS, VGD is going to reduce constantly. VGD is going to reduce constantly and at one point or other, it is going to cross the threshold voltage, right? So if I go on increasing VDS, then VGD will go on reducing, and at this particular value of VDS, you will have VGD is equal to V threshold. So if I consider this special case where VDS is equal to VGS minus VT, you are left with VGD is equal to V threshold. So that means at this particular voltage, between drain to source, the channel is completely blocked, and if you even increase the voltage a little bit, there is no channel existing between right near to the drain terminal. Okay, so the channel is has shrinked and finally completely gone off near the drain terminal. So what have we seen? VDS equal to 0, there was no current. VDS positive, the current starts increasing, but the channel starts decreasing, and at a certain value of VDS, the channel is completely closed. So if I now try to draw the output characteristics from this, you can expect a similar kind of output characteristics, right? What we have seen in case of JFET. So see, I have a particular value of VGS. Let us consider that VGS equal to plus 8 volt. I have applied. Okay. So if that is true, then for VDS equal to 0, the output characteristics is again a similar graph where you have VDS in the x-axis and ID in the y-axis. ID is the output current flowing in the circuit. VDS, the drain to source voltage, is the output voltage. This is the output characteristics. And say I have fixed my VGS at 8 volt. So if VGS is equal to 8 volt, then for VDS equal to 0, we had no current. That is fine. Okay. Then I started increasing VDS and the channel started shrinking a little bit to near the drain terminal, but the current was increasing. So the current was increasing linearly. This is the linear portion, right? But at a certain value of VDS, which is given by this relation, VDS equal to VGS minus VT. At that value, the channel got completely closed near the drain terminal, and there is again a knee-like structure, and the channel pinches off and the current saturates. Okay, so this voltage of drain to source voltage VDS is called VDS saturation. Okay, this voltage is called VDS saturation. And if you go on changing VGS to lower and lower values, the slopes get changed. Why do the slopes get changed? Because the channel width change, and the channel width area available for the electrons to flow reduces, and that means the slope will change of the graphs. So the slopes of each of these graphs will be different, and they will be saturating at different points. And a similar kind of a graph you can see what we have seen in case of JFETs, right? So as soon as it is equal to V threshold, which is 2 volt for this circuit, there is no current flowing, and we reach the cutoff region. So a similar kind of output characteristics, but a completely different kind of operating principle. That is how an NMOS works. Okay, enhancement type N-channel MOSFET. So we discussed it in detail today. Just go and read about it a little bit and try to figure out what are the main similarities and what are the main dissimilarities of this device with JFET. And I am giving you one homework that try to draw the transfer characteristics in the same way that we did in case of JFET, right? You just try to figure out the transfer characteristics where the x-axis will be VGS and the y-axis will be ID. Draw it in the same way, extending in the other direction, drawing like a parabola, you draw it in the same way, and try to see what is the difference that you see from JFET, right? So try to figure out what is the difference that you see from JFET. So I will stop at this point, and if you have any question, please ask.
Where is MOSFET used in real life?
Yeah, sure. MOSFET is basically, I mean, has replaced transistors everywhere. In all the VLSI circuits that we see nowadays, MOSFETs are the common amplifiers that we use nowadays. It is very much used. Anything else? Okay, so just try to read whatever we have discussed once. Maybe it is, I mean, it will take some time for you to get the entire point, and come back to me in the next class and ask if you have any questions, or we will move on and discuss about the transfer characteristics and also the other side of the story, depletion type MOSFETs, which are a similar device but works in a just reverse principle, where the channel will be there to begin with, and we will quench the channel, shrink the channel by applying the VGS. Okay, so we'll talk about that in the next class. So till then, bye then. Okay, see you all in the next class.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you,
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.
Thank you, ma'am.